So last day we started talking about the three basic types of mapping functions that are used. The question being asked here is when you have to copy a block of data from memory to cache, how do you decide where to put it in cache? And you might say, well, that's kind of silly, just put it anywhere. And in fact, that is one of the mapping functions, as we'll see in a second. But that's only one of three ways. There are more strategic ways of determining where to put stuff in cache, so that when you're trying to reference a particular memory address, you have some way of seeing whether it's in cache or not, right? And that's why we have these mapping functions. So the question being asked is when we have to copy a block of data, let me back up. A program's running, it needs a piece of data from memory. So an address, a memory address, is being searched for in memory, and we need the contents of that memory address. If we have cache in the computer, what the memory controller will do first is go to cache to see if that memory address resides in cache. If it does, great. We call that a hit, and we get it quickly, and we keep going. If that memory address does not currently reside in cache, we call that a miss. And now the memory control unit has to go to main memory, copy the block of data that contains that memory address, because we never copy just one memory address to cache. We copy a whole block of data that memory address resides in to cache, right? And that incurs what we call a missed penalty. It takes time to do that transfer from main memory to cache. We call that a missed penalty. And then we can take that particular word and read it into a register in the processor and process it, okay? So that's what's happening in general with cache. Okay, so when we copy a block of data from main memory to cache, where do we put it in cache? And that's what the mapping functions address. And so the first one we looked at last day was direct mapping, and I'll just briefly review that. Over here on the right-hand side is our main memory. And in this particular example, we have a 64K memory where the address of a particular word in memory is given by 16-bit address, okay? And the memory, the contiguous data memory locations are grouped into blocks, okay? So we have blocks. And in this particular example, a block consists of 16 words, okay? So 16 words of data is considered one block, and that's true in the main memory and in the cache. Okay, in this particular example, it's 16 words per block. And so in a 64K block, main memory, we're going to have 4,096 or 4K of these blocks, okay? Now, the cache is much smaller, okay? A block still consists of 16 words, but in the cache, this cache is only 128 blocks, okay? So we have from 0 to 127 blocks in the cache. Every block is 16 words. But the main memory has many more blocks than the cache does, okay? So if we have 128 blocks here in the cache, we're going to group the blocks in groups of 128 in our main memory as well. So from 0 to 127 in main memory, right? That's 128 blocks. And then from 128 to 255, that's another 128 blocks. And we're going to have 32 of those groups of blocks in the main memory, because 32 times 128 gives us 4,096, okay? And so in the direct mapping scheme, we're going to say that the first block in every group of 32 blocks maps to the same position in the cache, block 0, okay? So if during the course of program execution we need a word that's currently stored at this address, at a particular address here in main memory, we're going to check to see if it's here. If it's not here, we're going to have to copy this block to the cache. And the only place in the direct mapping function that we're going to copy that to is this position here. If there's already something here, it gets overwritten, okay? If we need a word out of here, and this block of data currently does not reside in the cache, then this block of data has to be copied to the cache. The only place it can be copied to is there. If the word of data we need is here, and it doesn't currently reside in cache, then this block of data is going to be copied to cache. The only place it can be copied to is here. Okay? So that's what we call the direct mapping scheme. So we can then divide up our memory address. In this case, we have a 16-bit address for every word in memory. Okay? And first of all, in every block, there's 16 words. So if we're looking for a particular word in a block, we need 4 bits, because 2 to the 4 is 16. We need 4 bits to specify which word in a block we're interested in. Okay? We also want to know which block the word is interested in. Okay? Now cache, there's 128 blocks in cache. 2 to the 7 is 128. So these 7 bits will tell us which block position in cache we should look for this word in for. We should look for this word in, sorry. Okay? Now finally, there's 32 blocks in memory that all map to the same position in cache. So if we're looking in this block here in cache, we want to know which one of these 32 is currently residing there. We use the tag for that. 2 to the 5 is 32. Okay? So if this particular block is currently residing in this position here in the cache, okay, and we need a particular word in this block in our program, then the address for that word, these 4 bits will tell us which of the 16 words in this block we're looking for. These 7 bits will tell us which block in cache to look for this word in, okay? Because this block here will be written to here, right? Which would be block 0, so these will all be 0. And then finally, we got to know, is this the correct one of these 32 blocks? That's what the tag tells us. So when this block gets written over to here into cache, it's the tag, these 5 bits, for all of the 16 words in here will be exactly the same, right? The 5 most significant bits in the addresses of these 16 words in this block will all be the same, and that tag will be written somewhere here beside it in cache. So now if we're looking for this particular address, we look at these 5 bits, sorry, we would look at these 7 bits first to see which of these 128 blocks we should check. And then we look at these 5 bits in the address that we're looking for, and we compare it to, for instance, if this is all zeros, we're looking at this block here, and then we compare these 5 bits in the address we're interested in, and we compare it to the tag that's currently associated with that. If it's a match, we know it's in cache. Yeah.
So how did you get the 5? You went 16 bits minus 7 minus 4.
Right.
Okay. And to get that
and it's not just that, it's the fact that we have 32 blocks in our main memory that all map to this position, and 2 to the 5 is 32.
Right. And to get that 32, you went 4096 divided by 128.
Yep.
To get 32.
Yep.
So we get 32,
Yep.
and that's 2 to the 4.
Yep.
And then, okay,
Yep.
2 to the 7, and then 2 to the 5.
Yep. Okay? So that's direct mapping. Okay?
Is it different for set associative?
Yeah, it's going to be different.
Okay.
Any more questions about this first, and then we'll move on, because we did this last day, so that was a review. Hopefully a little bit clearer. Yeah, go ahead.
What does the J modulo 128 refer to?
It just means that you've got 128 blocks here. You've got groups of 128 here, but you only got one group here. So it's just referring to the fact that block 0 here maps to here, and then block 0 plus 128 also maps to here. And block 128 plus 128, which would be 256, also maps to here. Okay. Place for any of these 32 blocks where they can go. It's right here. They can't be copied here, 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 or here, right? It's these light blue ones that can only be copied here. It's these gray ones that can only be copied there. Only one place in cache that a particular block in main memory can go. If you go back to here, you look at these 7 bits, you know already which block here you have to check, and you only have to check that tag. The advantage of this one. The advantage of this one is it's relatively simple to implement in hardware, okay? There's not a whole lot of decision-making that has to happen by the processor or the memory unit when it is mapping one of these to here. It's been pre-coded or pre-designed in hardware that this guy always goes there. Very simple, okay? There's no question. Whereas in this one,
Or it's like block 148 and cache at the same time, because they would need to go in the same spot?
well, they can't be in cache at the same time.
Okay, so
Yep.
you're just not allowed to do it?
Exactly.
Okay.
Yep. So if this one is currently in this position, and you need a memory address from here, that's a miss. And so now this block will have to be copied into cache so that you can get that memory address. Yep. Or in this case, okay, I gotta copy this one over, it's gotta go here, there's already a different one here, well, there's no replacement strategy here. There's only one place this block can go, it's there, that's where it goes. But in this, so opposite end of the spectrum. So direct mapping, there's only one place in cache that a particular block can be copied to, right? There's only one. Associate, total opposite. They can go anywhere. So we got the same example here, we got the same main memory, 4,096 blocks, but we don't have to group them now, because any one of these blocks here can go to any one of the blocks in cache. Which, if you didn't know anything about mapping functions, is what you would probably assume actually happens, right? Now, if we need this particular, if we need a word from here in this block and it currently doesn't reside in cache, well, let's just put it in cache anywhere there's an open spot, okay? So that's what we call associative. It's the most flexible. Any memory block can be mapped to any position in cache. So what would a 16-bit address now in this particular example look like? Well, again, we still need the 4 least significant bits to tell us which of the 16 words in a particular block we're looking for, okay? So each one of the 16 addresses in this block of data here will have a unique combination of 4 bits, and 4 least significant bits, 2 to the 4 is 16. And then we still have to have a way of seeing if the block of memory in which resides the address we're interested in, whether that block of memory is in cache. So we use a tag for that, okay? But we don't need a block field here anymore, because any one of these blocks here could be in any of these blocks here. But we still need the tag field, so the other 12 bits, the most significant 12 bits, will indicate which one of these 4,096 blocks is currently in a position in the cache, right? Because 2 to the 12 will give you 4K. So now, if you want to know if a particular word at a particular, if you want to know if a word at a particular address is currently in the cache, you look at its 16-bit address, you look at the tag here, and you compare that tag to all the tags of the blocks that are currently stored in the cache. If there's a match, you know that the address you're looking for is currently in cache. And then you look at these 4 bits, and that'll tell you which one of the 16 words in that block is the address you're looking for. Yes, sir?
Do both the mapping, like direct mapping and associative mapping, take the same amount of time to retrieve anything from memory?
I'm going to say no, although it's probably very slight in difference. Because here, this one, you have to compare this tag in your memory address that you're looking for to all of these tags. Now, they have clever ways of doing that. They can do it in parallel. So the difference in time is probably slight. Okay, so yeah, an associative search, you search all the tags in parallel. You compare all of these to this one to see if this address is currently in cache. Okay, but of course that requires hardware. So yeah, you can do it faster, but it's a trade-off. You need the hardware to search all of these tags in parallel to see if it matches this tag in the address that you're looking for. Okay, so associative is pretty easy to understand. Any questions about that one? Okay, so the third one is you're going to have to not you, but the processor or the memory unit is going to have to decide if it's copying a block from here to here, where to put it. Okay, that requires some thought on the part of the processor. Okay? So in this case, I'm copying block 1 over. Let's just pick any one of these 128. They're all full. I'm just going to randomly choose one. That is actually a valid strategy and apparently works rather well, okay? A decision has to be made and a combination. So, you know, somebody at some point said, well, let's put the two together and maybe we'll get the best of both worlds, right? The associative is very flexible. The direct is very simple to implement. What if we combine the two? Yeah.
We should run into a problem with the direct mapping, like say,
Okay, so set associative is a combination. So again, there are only certain positions in cache where a particular block in main memory will be mapped to, like in direct. But like associative, there's more choice. So in this particular example, and this is just an example, right? In the direct method, there's only one position where a particular block from main memory can be copied into cache. In this particular, which is called a two-way set associative, there's two positions in cache where all of these blue ones could be mapped to. Okay? So there's a little bit more flexibility. You need an address from here, but this block is currently occupying this position. Well, this position might still be open, so yeah, you can copy this one into there. And now you have this one and this one both in here. Okay? Again, here a block is 16 words again. Okay? But now because we have two positions, we're going to divide our blocks in main memory. We still have the same number of blocks, 4,096, but instead of grouping in groups of 128, we're going to group them in groups of 64 because we have twice as many positions to hold blocks in a particular position in the main memory. Okay, so instead of block 0, block 128 both being mapped just to this one, now it's block 0, block 64, block 128, block 200 something, can go to either one of these two positions, right? So all of these blue ones can go to either one of these two positions, okay? So a little bit more flexibility than direct mapping, but a little simpler than associative. Where in associative, they can just go anywhere. Here, again, they can only go to one of two positions, right? And obviously all the light blue ones, not every 128, but now every 64, modulo 64, are being mapped to either one of these two. So our 16-bit address, again, the 4 least significant bits, we still have 16 words. Again, this is in this example, 16 words per block. So we still need 4 bits to determine which of those 16 words we're interested in a particular block, okay? We still have a tag because we still need to determine if the block we're looking for in main memory here actually exists in cache, okay? Now we need a 6-bit tag. What's 2 to the 6? 2 times 2 is 4, 8, 16, 32, 64, right? Because we have, now we're going to have 64 of these dark blue blocks here that all map to one of these two positions, to either of these two positions, I should say. Okay? So 2 to the 6 is 64. So this tag is going to tell us which of these 64 dark blue ones are perhaps sitting here or sitting here. Okay, so again, this tag is compared to the tag of each of these. And in these groupings, we call them sets. Okay, so now this is a two-way set associative cache, which means there's 2 block positions in cache that a particular, or that these 64 could be copied into. A 3-way means that the set consists, there would be 3 blocks here where any one of these could fit into. A 4-way, etc. Okay, yeah.
Is the tag linked to the cache position or is it linked to the block? So
The tag is this is linked to, this 6-bit combination will be unique for each one of these. Yeah. Actually, for every one of these blocks. Okay? All 16 words in here will have the same 6-bit tag. All 16 words in here will have the same bit tag, which will be different than this tag. Right? Every block here, all the words in each block will have the same tag, but the tag will be different for each one of these blocks. okay, because it's the 6 most significant bits. Okay, and then the 6 bits in the middle here are going to tell us, pardon me, which set to look for this memory address in, okay? In the direct mapping method, this was a block because there was just one block, there was only one block position where any particular block here would map to. Now, in this case, we have to know which set to look in, where a set consists of 2 blocks. 2 to the 6, again, is 64, right? There's 64 sets of 2 blocks because this is still 128 block cache. Okay? Any questions about that one? So, if you got a 16-bit address and you want to see if it's in cache, you would check the set. Okay? If these are all zeros, you know you're interested in set 0. So you go to the set 0, you go to these 2 blocks, you take the tag of the memory address you're interested in, you compare it to these 2 tags. If there's a match, you know this address is currently in cache. You got a hit, away you go. If it isn't, now you're going to have to copy. You know that that address is not in cache. You're going to have to go and get that address from main memory. Not just that particular address, but the whole block that it sits in, because we don't copy just one address to cache at a time. We copy a whole block, and we're going to put it into one of these 2. Okay? So those are the 3 basic types. Well, it doesn't really matter. It doesn't matter. Let's assume that you got to copy a block of memory over to cache, and the cache is currently full. There's something in every block position in cache, and the memory address you're looking for isn't in any of them. Okay, well that means we're going to have to copy a block of data over to here. Well, in this case, if I'm copying block 64 over to here, which one of these 2 do I replace with my new block of data? That's a decision that has to be made. Now, you could just say, I don't care, let's just randomly pick one of the 2. Or, in case also a decision has to be made. We call it, there's going to be some control bits associated with all of these, and that control bit might be set to a 1 or a 0, and then the processor will look at all of these for, if I'm choosing which one of these 2 blocks to write a new block from main memory into, well, if this block hasn't, the words here haven't been used in the longest time, its control bits will be a certain value, and that's the one it chooses to overwrite with the new block from memory, okay? The one that has been used least recently. If I keep using words in this block here, I don't want to get it out of cache, right? Because I'm using the stuff out of here. So, but if I haven't used the data in this block in the longest time, well, that's the one I'm going to overwrite with new data from the main memory. Yes. The question then comes associative, particular block, 0.5. So let's finish off here. Cache always takes so long. Okay, so what happens on a write? So we've got cache. What happens when we want to write a value, a new value to a particular memory location in our main memory? Okay? So the processor has calculated some number and it wants to store it at a particular memory address. Well, if that memory address is in cache, what do? Would we write the new number in cache only? Or would we write it into here? That memory address is always in the main memory, right? It's always here. It might be here if that block of memory has been copied over to the cache. So if we've got a new value for a memory address, do we put it just here, or do we put it here as well? Okay, so there's a couple of ways to do it. First, there's write through. So the block is written to both, or you could say the word would probably be more accurate here. The word is written to both cache and to main memory. Okay, so you've got a new word for a particular memory address. If that memory address has currently been copied over to cache, you copy it here and you copy it right away to main memory. Because at some point in the future, you might need this new number at this address. If that address is no longer stored in cache, you got to get it from main memory. So it eventually has to end up here at some point, okay? Well, that is, of course, a little bit slow because writing to main memory takes time. So you don't want to, you don't want to hold the processor up. Writing to cache takes no time at all. writing it through to the main memory takes time. You don't want the processor sitting here waiting until this memory location has been written to, and then it can go on, okay? So often they use a write buffer, which means, okay, you write it to cache, that takes no time. You also stick it in this buffer, and you tell the memory controller, when you got time, write this to that address in the main memory. And then the processor goes off and does the next thing it needs to do. Okay, so it sticks it in this buffer, and the processor forgets about it, and the memory controller takes care of it now, and at some appropriate time, it'll write it into here, okay? Or what's called write back or copy back means that that word, or that new word gets written to the memory address in cache, and then we don't worry about writing it here. We actually set a bit here called the dirty bit, which means this memory address contents has been changed. It's dirty now, if you want to call it that, with a new value, okay? And again, main memory could be updated later. You don't actually update it here until the block here that contains this updated word gets written over, right? At some point, a new block is going to get written into that place in cache. Before that happens, though, you want to transfer the new value at this memory address that you just wrote there. You want to transfer that to the main memory. Now you can overwrite it here with new data from a different block in main memory. Okay, so we call that write back. It uses a dirty bit. So write through is simple, right? We just write it through right away or stick it in this buffer. Write back, no writes to memory for repeated updates to a word in cache, because maybe you calculated a new value for this word, you stored it in cache, and maybe 2 instructions later you need that new value again, okay? Well, you just read it from cache. Maybe 2 instructions you need it again, you read it from cache, right? Maybe 2 instructions later, you change it again. You write it to cache and you leave it there. You don't do this time-intensive operation until you're kind of done with that word. And then it can be written here.
So
Okay.
that's write back.
That's write back. That's this one here. That's the advantage of it. You don't do this right here until you absolutely have to, basically, okay? Because again, it's this, that writing and reading from here that takes time. This is the bottleneck in a computer. So we want to avoid doing that whenever possible. To this picture, we're reading something from main memory here. It could be written into cache and in a parallel path be read into the processor at the same time. So that's called like that. I would like, or set it, that's least about a read. So we're reading something from memory. So if it's not in cache, we call that a miss, right? A read miss. So obviously the block that contains that address you're interested in has to be loaded from memory into cache, and then we forward the particular word we're interested in from cache to the processor, okay? Alternatively, the word can be sent to the processor as soon as it is read from the main memory. So we call this load through or early restart. Okay, so if I load through or early restart. So of course that reduces the wait time because you don't write it into cache first and then read it from cache into the processor. It goes straight from main memory to the processor, but of course you need more hardware to do that. So that's the cost of that. To talk about this first. Okay, well, if the address you're looking for is not in cache, and you've got to copy a block of data to cache, from main memory to cache, how do you decide where to put it? Well, in the direct map ahead to a replacement algorithm, okay? And again, a random algorithm actually works pretty good, okay? But people have tried to be a little bit more strategic because remember, the whole idea about cache is that if we are at a current place in our program, we're at this particular instruction at this address. Well, we know that because of the principle of locality and the way programs run, we're going to need the next instruction at the next address, and then the next instruction at the next address. We're going to need the data all in that block. That's why we copy a block of data over, right? And if we're at this point in our program, what are the odds that we're going to need something at this point in our program? Pretty low, right? So you don't want to just willy-nilly replace blocks in cache. You want to have some strategy to it so that you don't overwrite a block in cache that you're going to need again very soon in your program. Because then what happens is, well, now I got a cache miss again. I got to go back to main memory, and I got to write that block back into cache. I just had it in cache. I replaced it with something else, but very shortly I needed it again. So you might not want to overwrite that one. You might want to overwrite a different block in cache, which you're not going to need anytime soon. Okay, so that's the whole idea about these replacement algorithms, and they can dramatically affect system performance because, again, there's a huge penalty that happens when you get a cache miss. So we want to avoid cache misses as much as we can. Okay, so probably the most common is the least recently used replacement algorithm. So I've got to copy a block from memory into cache. My cache is currently full. Which block do I choose among the choices I have to replace? I'm going to replace the block in cache that has not been used in the longest time, okay? Because if I haven't used that block in cache very recently, chances are I'm not going to need it very soon again, so I might as well overwrite it with my new block from main memory. Okay, so we call that least recently used. And there are control bits that are used that are associated with each part in cache, which keeps track of that. Every time a memory address is accessed in cache, recently used, okay? Another strategy is to remove the oldest block. And by oldest, we mean the one that's been in cache the longest. That doesn't necessarily mean it's the least recently used, right? We might copy a block of memory into cache a long time ago in our program, and we might be using it right now, okay? But if it's the oldest block, it would get replaced with a new one if we need a new one. So that's maybe not the best. This is by far the most commonly used because it makes most sense with the whole locality principle, okay? And some people have suggested too that least recently used actually works a little bit better if you throw a little bit of randomness into it. Every once in a while you just pick a random block instead of, that apparently seems to improve things a little bit. So there's researchers who spend their whole careers trying to figure out what's the optimal way, what's the best replacement strategy to replace blocks in cache when you write new blocks in. Okay, so that's what we call replacement algorithms. So there are a number of examples in section 8.6.3 of the textbook. I'm not going to take the time in lectures to go over it. It's easiest if you read. It's only about 3 pages in the textbook. There's 3 examples there. I can't emphasize enough how important they are for the purpose of, first of all, doing assignment number 3, and second of all, for the final exam. Okay? So they're an example of the direct method, of the associative mapping function, and the set associative. There's an example each. They're relatively simple, okay? It takes a little bit of time to sort of wrap your head around what's going on. Once you figure out the first one, the second and the third one come pretty easily, okay? So please, please, please study those, especially before you do question 8.5, thank you. If you haven't tried 8.5 yet on assignment 3, don't try it until you've studied these, okay? You won't know what to do. So while I'm talking about 8.5, it's a little bit, at first glance, it looks a little complicated, but it's not that bad after you sort of wrap your head around it. What it's asking you to do is calculate the execution time of a program. Doesn't give you the instructions. The instructions, what type of instructions they are, meaningless. It gives you a figure, and I really should have taken a scan of it, put it on my computer. But I'll just give you the gist of it now. Maybe on Friday I can elaborate a little bit more if you want me to. It gives you a figure that shows you the memory addresses for instructions in an assembly language program. It doesn't show you the instructions, that's irrelevant. It just shows you the addresses, okay? And there's a couple of loops in this program, and it shows you where the loops are. You know, when you get to this address, it loops back to here. And it asks you for an instruction cache. So that means a cache memory that only holds instructions. It holds your program, not data. So a lot of caches will be divided into data caches and instruction caches. The instruction cache only holds instructions of your program. The data cache only holds data, okay, that your program uses. So in 8.5, it's only asking you to consider an instruction cache, and it tells you how big and all the rest of it. and it's the direct mapping function that's used, I believe, I think. Okay, and it asks you, okay, here's the program, how long is it going to take to execute? And it tells you, you know, memory access time is tau seconds. Doesn't matter what the number is, they just say tau. A cache miss is 80 tau. Okay, so it's when you're looking for a particular instruction, you always look in cache first. If that instruction's not in the instruction cache, you get a miss penalty, which in this case is 80 tau. Okay, so what you have to do is you have to look at this program, and you have to, given the cache size that you're given, and they tell you how many words in a block and how many bytes in a word and all the rest of it, you have to figure out, okay, I've got statements here, I've got instructions here in my address, where would these instructions be copied into cache? Okay, assuming that you start at an address of 0 and go up. So I don't remember the details, so I'm not even going to say the details because I'll probably say it wrong. But you got to look at these instructions, and the first thing you have to ask yourself is, where would all of these instructions fit in the blocks in this cache? Okay? And then you have to ask yourself, okay, I'm going to start at the beginning of the program execution. You always assume that when you start at the beginning of the program execution, that the cache is empty. There's nothing in it. None of your program is in the cache. All of your program is in memory, main memory. So that means the very first instruction that executes is going to incur a miss, right? Because there's nothing in the cache yet. So that means right away you've got one miss. So when that first instruction happens, it's a cache miss, which means the block of instructions that instruction currently resides in now get copied into cache, and they occupy a particular position in cache. Okay? So that means the next few, however many that is, the next few instructions will all be in cache. So there will be no miss. Okay? When those instructions are executed, there will just be the memory access time of reading that instruction from cache for each one of those instructions. Eventually, you'll get to an instruction in the program which is not in the block that's currently in cache. Now you got another cache miss. Another block of instructions gets copied into the next block in cache. So you got to work your way through to figure out, okay, and then eventually you'll have all the blocks filled in your cache. And then at some point, you know, it loops back. That's why these questions always have loops in them. It loops back. Oh, I need this instruction again. Well, that instruction got overwritten, or maybe it didn't. If it didn't get overwritten, it's still in cache. Good, no cache miss penalty. But if it is overwritten, if it got overwritten somewhere along the way, now I got another cache miss. So you got to figure out how many cache misses will happen as you go through this program. Each one of those is 80 tau. And then you have to add up how many memory accesses. So how many instruction executions do we have? How many instructions do we have to read? Okay? Once they're in cache, it costs tau seconds to read an instruction. So you got to add up how many instruction executions do I have? And each of those costs a tau. Now the only wrinkle in that problem, which it's not very clear, is that the tau, well, I have a solution from the textbook publisher, right? And I kind of don't agree with the solution because they say the memory access time from cache is tau seconds, but they assume that that's per byte. And if an instruction is 16 bits, that's, how many bits in an instruction? 32 bits in an instruction, they say. So that means an instruction is 4 bytes. They say that to read in one instruction of 4 bytes, it actually costs 4 tau. So the tau they're using is per byte read from cache. I think that's kind of silly. I think it should be, tau should be the whole word. But if you're doing that, if you haven't done that question, when you're adding up how many times or how many memory accesses from cache you have, it's going to be 4 tau per instruction, okay? Or 1 tau per address because it's byte addressable memory. Now, maybe a lot of that doesn't make sense to you until you actually look at the question. But don't worry about the tag field and the block field and the word field. You don't have to figure, because they don't actually tell us how long the addresses are, how many bits the addresses are. So you can't even figure that stuff out, and you don't need it. All you're figuring out is how many times are these instructions being executed and how many cache misses will happen. So you gotta lay it out. You gotta go through the program and you gotta figure out, okay, when these instructions are happening, that'll be copied into that. And now all the instructions in that block, no problem, no miss. Oh, I ran out, now I gotta copy the next block into cache. That's another miss penalty that I gotta add up, et cetera, okay? Yes, sir.
So is it 80 tau per block or per address when you miss?
Another good question. So you're moving along the program, okay, executing instructions that are currently in the cache. Finally, you get to an instruction in your program that's not in the cache, okay? That's going to incur an 80 tau miss penalty, and it's going to copy the whole block that instruction will be the first instruction in a block of instructions that gets transferred over. So that 80 tau is per block, okay? Now, the next instructions keep executing, well, they're in cache because they were transferred over in the same block. At the end of that block, we run out and then the next block. So it's always a block that gets copied over. Yeah, a very important point. Yeah,
You made an interesting comment there which surprised
hopefully it was true. Go ahead.
You said that you're going through a block and you're looking for the next thing. And when you move a block, it's going to be the very first item in the block. Is that all? That doesn't sound like that should be true.
You're correct. It isn't.
Okay.
In a straight line, so the question is, when you copy a block over, does that only happen when you're trying to access the first instruction in the block? That's only true if your program is a straight line sequencing with no branching. Then that'll always be true. But in these problems, there's always a loop, right? So when you loop back up, you might loop back to an instruction that is, its address is in the middle of a block. You're quite right, in which case, oh, but that whole block, the instructions before it and the instructions behind it will be copied over. Yeah. Okay, so that's replacement algorithms. Okay, and we talked about replacement algorithms. So the 3 C's of cache misses: compulsory, conflict, and capacity. Compulsory means when your program starts, you know you're going to have a cache miss right away, right? Because your cache is empty. There's nothing in it. So that's what we mean by compulsory. It's a cold fact of life. There's nothing you can do about this. But of course, if you're running, if your application is an operating system where you've got billions and billions of instructions, well, when you first start up your computer, that's when you get the cache miss. After that, it's not an issue. Conflict or collision. So you have multiple memory locations in main memory that all map to the same part in cache. Obviously, that can slow things down, or we call it a conflict. The way to do that is increase your cache size, so there's more places where you could put a particular block from main memory, or you can increase the associativity. You increase the number of blocks in a set in cache. Again, giving more positions, more options where you can copy a block from main memory too. Of course, capacity, cache cannot contain all blocks accessed by a program. The cache is always smaller because it's expensive memory. You make it as big as you can, but there's a limit. Okay, and let's just talk about this quick because you need this for the assignment. Estimating the average access time of anything in memory, okay? Well, it could be in cache, and we typically have 2 levels of cache. We have level 1 and level 2, typically, okay? So if you're looking at the average time it takes to get something from memory, well, it could be in cache 1, it could be in cache 2, or it could be in neither, okay? So if H1 is the hit rate, that means, what percentage of the time what you're looking for is in cache 1, that's H1. What percentage of the time that you're looking for something, it's in cache 2, that's H2. C1 and C2 are the access times to get something from cache 1 and cache 2. M is the access time to get something from main memory. If it's not in cache 1 and not in cache 2, well, then you got to go to main memory. This is how long it takes to do that. So the average time is going to be a function of all of these, and it kind of makes sense if there's 3 factors. Here, it's in cache 1, it's in cache 2, or it's in neither, and you have to go to main memory. Okay, so it's just probability. Well, if it's in cache 1, it's the hit rate times cache 1, the access time. Plus, if it's not in cache 1, 1 minus H1 is the miss rate for cache 1, times the hit rate for cache 2, times the access time for cache 2. So this is how much how much accesses to cache 2 contribute to the average access time. And finally, if it's not in cache 1, the miss rate is 1 minus H1, 1 minus that rate, and it's not in cache 2. So times that by 1 minus H2, that gives us the miss rate for cache 2 times the access time from main memory. So this is the contribution to the average access time of getting something from main memory, of getting something from cache 2 and cache 1. So you're going to use this in one of the assignment problems. We'll stop there and see you Friday. What do we got left? Much to still do today.